and I'm going to give this talk on handling uncertainties in cyber-physical systems during their operation with digital twins. And I am a research scientist at Simula Research Laboratory in Norway, and this work is together with my colleague Tao Yue, who has position both in Simula and also at Nanjing University of Aeronautics and Astronautics in China. And the work we are going to present is funded by one of recently started EU project, which is called Adaptness. So I will start with giving a brief introduction of the project, followed by putting this work into context of the project and what do we plan to do in the context of this project. So first I'm going to talk about the project Adaptness a bit, and the overall objective of this project is to develop a workflow to speed up the software releases of cyber-physical systems in operation while guaranteeing its reliability. So what actually we want to do in the context of this project is to take the concept of DevOps, that is development and operation, and try to map it to cyber-physical systems or systems. And what we want to achieve is to cover both development and operation phases, and so that our ultimate aim is to improve the reliability and the dependability of these kind of systems while they are in operation. And the project has several sub-objectives, and the first objective is that we want to demonstrate that by developing the new method for DevOps for cyber-physical systems or systems, we can significantly improve the quality of cyber-physical systems or systems. Second, we want to demonstrate that we can reduce the time and cost for recommissioning of software releases of cyber-physical systems while guaranteeing its reliability. So we want to measure how much time we can reduce in recommissioning of software releases. Third, we want to improve these synergies and collaboration between industries and academic partners. Given that it's a project which is under industrial leadership part of EU Horizon 2020 program, so our aim is to work very closely with industry so that we can develop the method that can be evaluated in the use cases which will be provided by our industrial partners. So now I'm going to give a brief overview of how the overall consortium of the project looks like. And this project is coordinated by this university in Spain, which is called Mondragon University, and it's located in the Basque Country. And together with Mondragon University, we have several other research partners, including Simula, Ikeland Corporation, Mälardalen University in Sweden, and Technical University of Vienna in Austria. And all these research partners have a clearly defined research task that they want to perform in the context of this project and want to evaluate the performance of their developed methods in the context of industrial use cases. In the context of this project, we have access to two use cases which are provided by two companies. The first use case is about elevators, and it is provided to us by Orona, which is a company located in Spain. And second use case provider is Bombardier, which is Bombardier Transportation, which is located in Sweden. And together with these two use case providers, we also have two other industrial partners called Ulma Embedded Soft Solutions and Easy Global Market. And these two partners will provide us other tools and technologies which are required to implement our methods that we will develop. So if you look at this, the overall consortium is a mix of research partners, use case providers, and tools and technology providers. And now I'm going to briefly discuss about our first use case, which is about elevators. And if you look at this picture, this is one of the installation of Orona, which is used for performing different experimentation in their current practice. An elevator can be considered as a complex cyber-physical system because it consists of a lot of sensors, actuators, and increasingly these systems are connected to internet and they can provide live data for maintenance and other kind of activities. And if you notice that humans are one of the key aspects in these elevators because they interact with it all the time. And as we know that human behavior is highly unpredictable and difficult to predict. And Orona has about 250,000 lifts installation all over the world, and people have been using this quite a bit in all over the world. And then increasingly, as I mentioned, that these elevators are autonomous, and it means that depending on the dynamic behavior of how people are using the elevators, it has to adapt its behavior itself. And for example, a typical elevator can have up to 500 kilo lines of code implemented as part of its implementation. And the second use case which is provided to us is from Bombardier Transportation, and this is about train control and management systems. And I present there this one of the picture, this the one I took from one of the references, but it fairly defines what actually happens in Bombardier's transportation system as well. So as you can look around this picture, you can see that train control and management system is a very complex system that manages all these different parts, hardware, software, and mechanical parts which are shown in this picture. For example, there is a uh, temperature control, there is a passenger information system, diagnostic, lighting management, water tanks, and you can see that there are a lot of different components, and this system is responsible for managing a very heterogeneous, diverse set of components to ensure that the trains are performing their operations safely, reliably, and so on. And this can be considered as one of a very complicated example of cyber physical system to system, because train itself consists of many different systems, sensors, software systems, and so on. So the train control and management system in the context of Bombardier is built on an open standard IP technology, and the aim is to provide an easy integration of all different kind of control and communication components which are presented on the train on board. And TCM acts as a center of communication system that controls the train. And the aim of TCMS is to control all the train functions either in a controlling or a supervising capacity. And we can look at that there are many different examples that exist for this train control and management system. For example, collecting line voltages, controlling train engines and brakes, opening and closing the train doors, and upload of dynamic data, and so on. So you can see that this is a very complex system which is very important, and it's like the backbone of a train, and it's important that this system works very reliably and safely. So now, as we see in the topic of the project, that we want to determine uncertainties in cyber physical systems by making some sort of digital twins of these kind of systems, and that I mentioned. So first of all, I would like to talk briefly about what do we mean by a digital twin for a cyber physical system. And if you look at literature, you can find a lot of different definitions in the literature, and I'm going to use one of a typical definition, or very commonly used definition, which is that digital twin is a digital replica of a living or non-living thing. And this definition is so generic that it can fit anywhere. It can fit for a cyber physical system, it can fit for a human body, it can fit for any other software systems as well. And in terms of our context, we say that a digital twin is of a cyber physical system can look like this diagram. For example, on the left side, you can see that a cyber physical system consists of different hardware, software, and they also employ network communication to coordinate different components, communication between different components. And of course, cyber physical system interact with the physical environment, for example, humans and other physical aspects. And on the right side, you can see that a digital twin could be think of as a live model of a CPS. And a digital twin can have two key components. First is called functionality, and the second thing is called management. So since we're calling of digital twin as the live model of a cyber physical system, so it means that data should be continuously coming to digital twin, and the digital twin, that is the live model of the CPS, should be up to date to represent the most up-to-date state of the cyber physical system. So that's why you can see this arrow going from cyber physical system to digital twin. And then if you see that, so we have at this moment a up-to-date state of model of a cyber physical system. So it means that on top of that, we need to perform some functionality to the system. So there can be different kind of functionality that you can perform. For example, you can perform runtime verification, you can do forecasting, you can do predictions, and so on. And depending on the results of those functionality, you can take some even actions on cyber physical systems. And the examples of these actions could range from simply, for example, raising a notification to the operator to take some action, or it could be a very sophisticated autonomous action that can be automatically performed by digital twin to prevent, for example, CPS from failure and so on. So as I mentioned, there could be different functionalities can be supported by digital twin. For example, simulations and predictions based on historical batch data and live data. You can perform very sophisticated verification and validation methods such as testing and verifying CPS online at runtime. And increasingly, people are planning to use visualization methods such as augmented reality, virtual reality to support digital twins functionality. Recommendation method, how should, based on the current digital twin, how can you provide recommendations to build new cyber physical systems, or how you can improve the development processes, optimize revenue, and create new business opportunities, and so on. So there are a lot of things that you could do with digital twins. So now coming back towards our topic, that we want to employ the concept of these digital twins to discover uncertainty in cyber physical systems. And in particular, in the context of this project, we want to do this uncertainty discovery in the context of the two use cases, that is elevators and train control and management system, to detect uncertain situations and enable cyber system through digital twins to prevent any unsafe situation that could happen because of those uncertain situation detection. So, and now one can say that why we have to deal with uncertainty, and would like to mention that uncertainty is an inherent characteristics of cyber physical systems. It's mainly due to it because of the several factors, but one of the key factors that makes the operation of these cyber physical systems unpredictable is the physical environment, because systems have to interact with the physical environment with sensors and actuators, and those kind of things are very unpredictable. And even if you make know a lot about the environment, you cannot guarantee that how the environment is going to behave during the operation of cyber physical systems. And then the cyber physical systems use communication networks or communication. So this means that there will always be packet loss, there will always be loss of connection. So how your cyber physical system will deal with such kind of uncertainties? And a lot of time, these cyber physical systems are built by buying third-party components with very limited or no access to these components, and then it's very difficult to see how these components are going to behave under different conditions. And then if we look at cyber physical system, it's a mix of software, hardware, agents, and so on. So it's a mix of different interdisciplinary things that are happening. And another thing that increasingly introducing much more uncertainty in these systems is the use of machine learning algorithm. For example, deep learning algorithm, deep neural networks, or deep learning that, and whose behaviors are very difficult to predict as well. So this means that because of all these factors, the behavior of cyber physical system is uncertain, and what we want to ensure that because of this uncertain behavior, the system should not fail, because this is a lot of these systems are very critical. And this is the aim of this topic, is to somehow apply different kind of methods during design time and the operation time of a cyber physical system to detect and prevent unsafe, uncertain situations. So in terms of, so if you look at that, this diagram specializes our diagram of a digital twin that we presented in the previous slide. And we can see that a cyber physical system we have, which is in operation, for example, And digital twin is continuously receiving data from digital twin, and it takes action on the cyber-physical systems. And as we mentioned, that a digital twin composed of a live CPS models, which are for example, shown on the right side in the dotted box, and it is also composed of, in this context, uncertainty discovery mechanism, which are performed on live CPS model. So what you can see from this diagram is that instead of having interacting directly with cyber physical systems, we are performing this uncertainty discovery on the live CPS models. And since these digital twin will be deployed at somewhere where we have much more high computational power, we can do much more complex and detailed analysis as compared to what we could do on the live operational CPS. Because if we try to do these kind of activities on the live CPS, we might end up interfering with the normal operation of the CPS that we would not like to do. So now moving towards our first approach that we're going to develop in this project is uncertainty discovery at design time with digital twin. So we focus on both design time and the digital twin and the operation time of cyber physical systems. And this slide will focus on uncertainty discovery at design time. And the last slide, the second slide afterwards, will focus on operation time. So if you can look at this diagram, you could see that a cyber physical systems during design time can be in various phases. So for example, here on the top, you can see that I mentioned that a cyber physical system can be software in the loop. It means that we have some software in the loop. It means that software is real, but other things may not be real. And then we have hardware in the loop and model in the loop. So there can be different kind of configuration on which you can perform this uncertainty discovery. So let's start with, in this design time, we want to focus on two types of methods. First is on passive learning, and the second one is on active ML, active machine learning. So on the bottom of this slide, you can see that we have design time uncertainty detection. And what we would like to do is that we would like to exploit the logs and the data that are available to us from both Bombardier use case and also from the Orona use case. And we would like to identify some sort of rules, some sort of invariant detection from this data. And in particular, our aim is to look for something which happens unpredictably. For example, it happens 10% of the time, it happens 30% of the time, or it just happens sporadically, and so on. So we want to focus on learning some things which have some degree of uncertainty associated with it. And we call this passive learning because we would like to exploit the batches of data or already historical data that is available to us. And if you see that there's an arrow going from design time uncertainty detection with passive learning to test oracle, so it means that somehow we need to determine what is correct, what is not correct. And this will be provided by another of our research partner, which is Mondragon University, that will tell us what is correct, what is not correct, what is known, what is not known. And this technique could also rely on multiple things. So for example, if we have existing models from Bombardier and we have existing models from Orona, for example, some Simulink models or other design models, we could also improve these models based on this data that we have in the form of logs and data. And eventually the output of this activity would be rules, constraints, models, and logs. It means that we have trying to learn something new that we didn't know based on operational logs or test logs and so on. And in addition, this design time uncertainty detection will also produce recommendations to deal with unsafe situations. It means that if you look at test oracles, it means that we detect something, uncertain behavior, uncertain situation, and we need to see if it is safe or not safe. So, and test oracles in this case will help us to determine if it's safe or not. And if it's not safe, we will invoke some recovery mechanisms which will be implemented by another of our research partners. So an example could be of uncertain situation, for example, is in case of, for example, Orona, which is an elevator case, could be that if you press the button, the elevator doesn't open, the door doesn't open even if the elevator is the same floor, or the door doesn't close down. So, and a lot of these kind of uncertain situations have been observed in operation by Orona. and that they don't know why that is happening. So, and we want to focus on learning these kind of uncertain situations. Then the second part is about design time uncertainty detection with active machine learning. It means that instead of passively mining the data, we would like to take some actions on cyber physical systems in either in any of these configurations, for example, software in the loop, hardware in the loop, or model in the loop. So it means that we take some actions on the CPS, we get data back from the CPS, and then we keep doing this action until we determine something uncertain. And the key point here is that we need some sort of guidance. And what we are planning to employ is some versions of reinforcement learning. It means that we will define some sort of reward functions based on some heuristics, which tells us far, how near we are to determine something unknown that we didn't know. And when we say what unknown, it means that something that we already known from the design requirements of the system, and we want to somehow explore the behavior which was not described in the requirements or in the models or in the implementation and so on. And as a result of the application of this design time uncertainty detection, we would be able to produce some logs and models. And models could be, for example, logs would be showing that, okay, these are the actions we took in this sequence, and this is the uncertain situation that we observed. And this is the improved models that can be used, for example, for improved the system implementation, for testing, and so on. And now coming towards discovering uncertainty at the operation time with digital twins, this is how we would like to do. So if you look at this, that the difference here is that now, previously the cyber physical systems was not in operation. It means that it was in the design time, and it means that we were either trying to do in software in the loop, hardware loop, or model in the loop. But in this case, we assume that the cyber physical system, for example, the train and the elevators, they are in operation, and we are receiving live data from the systems. And if you look at here is that this digital twin capability, we can see that there are two parts, as we mentioned that in the definition of digital twin, that it can have a live model of CPS and it can have some functionality. So if you see that we have digital twin model learning, which we call, which will apply a machine learning, and it will take input existing CPS OS models if they are available, and also the models that we learned from the design time. And these two will be the key inputs that will be representing our digital twin. And then it means that and based on the data, which is live data, which is coming from CPS in operation, we would like to continuously improve the implementation of this digital twin, which is based on some sort of model learning. So it means that we keep improving the model that we have. What kind of model we will have, it depends on what is available from the both use case provider, for example, Simulink models, Modelica models, and so on. And then you can see that to improve the model, again, we need some sort of heuristics. Heuristics means that is the element I'm learning about digital twin, is it new or not? So again, we will employ some sort of these heuristic that I mentioned in the previous slide to continuously improve the digital twin models. And as a result of this digital twin model learning, we will output digital twin models. And then on this digital twin model, we will perform operation time uncertainty detection. And one thing I would like to mention that these models will be continuously updated and reproduced, because the live CPS will be continuously providing us data, and this will be producing digital twin, and as a result of that is giving as an input to digital twins model learning, and it will continuously produce digital twin models. And then if you look at digital twin capability, it will be performed on digital twins rather than real CPS OS in operation. And again, in this case, we will rely on test historicals to determine whether we have determined some uncertainty which is unsafe. And if it is unsafe, we will call different kind of recovery mechanisms. And we ask, for example, ask some notification to the operators to take actions or perform some autonomous actions to take care of unsafe situations. But the key capability, the key techniques, again, what we want to imply is the use of reinforcement learning, because we want to continuously take actions with digital twin models, and we get data from, as a result, we get data from digital twin models. We keep taking actions until we observe something which is uncertain. So Again, heuristics here will be how close we are to observing uncertain behavior. So you can see that we have a similarity here with the previous digital twin uncertainty detection, because there we are also applying reinforcement learning, we are applying heuristics, the same heuristics, but the only difference is that in the previous one we were performing this active learning on cyber physical systems or systems in SIL, MIL, or hardware in the loop, and in this case we are performing on digital twin models. This is the key difference between this, but of course the methods can be reused on the both cases. And same as the design time uncertainty detection, as a result of this, we will produce some logs which will show us, okay, these are the action performed, this is uncertain situation that we observed, and it used test historicals to determine unsafe situation. And you could also see that there is an arrow coming from CPSOS operation to digital twin capability. It means that this live data will also be continuously coming to digital twin capability. That will help us to detect that will help us to continuously detect some uncertain situations. So again, this is another key difference between the previous one. The previous one, the data was, this live data was not available. So in this case, this will be an additional input to our digital twin capability for operation time uncertainty detection. And of course, it will produce recommendations to deal with unsafe situation, including invoking recovery microservices. So this is how our operation time uncertainty detection looks like, and you can see that depending on our use case, we might have to we may be able to access cyber physical systems in operation for a smart part of the experiment, but it will not be always possible, because if it can interrupt with this operation. So what we do there for our experimentation purpose, we would also like to configure this cyber physical system in operation as with HIL, hardware in the loop, software or model of the loop, but it will be configured as it is in operation, because when the system is in operation, you can only get data from it in our context. So it means that we cannot take much actions on the system. So it means that we could also think about configuring HIL, MIL in exactly the same way as it's in a live operation to perform much more experimentation that we plan to do. So this is our operation time approach for uncertainty detection. And now I would like to uh, open the presentation for any discussions and questions that you can post uh, to me, and would like to answer them during our discussion session for the workshop. Thank you very much for your time.